Predict G from space geometry. Modern physics assumes that space is smooth and empty, but what if that assumption is wrong? If space has a real underlying structure, a true geometry, then the way information spreads through it should be directly related to that geometry. From that hidden diffusion behavior, we could predict the true value of the gravitational constant G, something no one in history has ever done. If you can calculate the geometry of the space network correctly, you could become the first person to derive G from first principles. This idea could become the foundation for your original physics thesis, and will show you where to find the full theoretical framework. The hidden geometry of space. For centuries, space was treated as a smooth, empty backdrop, something that held matter and energy. But information theory suggests that it must have a structure, a hidden network underneath, a structure that would subtly influence everything: how light travels, how gravity spreads, how information moves. After all, how does an empty void create distance? How does it degrade fields like gravity and electromagnetism? Can a true void really do all these things we see space doing? A discrete, quantized network model of space could reveal the true geometry of space, and unlock answers that continuous models can't explain. One discrete model of space has been calculated. So far, only one discrete model of space has been fully calculated. It's a simple network where each node connects to exactly 6 neighbors, forming an orthogonal, lattice-like structure. This geometry naturally produces an octahedral spreading pattern, where information flows outward along the 6 primary axes. In this model, information spreads outward with a diffusion rate of exactly 4r squared plus 2, 4 times higher than the traditional assumptions used in physics. But this model is static. It has no dynamic rule set to allow extra temporary connections. Without that flexibility, it cannot create a truly spherical diffusion pattern, the kind of structure that space likely has. Defining a dynamic spherical network could reveal even deeper insights, and that frontier remains open. Idealized reference models. To understand what a perfect geometry would look like, we can also consider 2 continuous models of space. First, if information spreads orthogonally but space is perfectly smooth, the expected diffusion rate would approach 4 times the square root of 3 times r squared. This reflects the surface area of an idealized octahedral shell. Second, if space is completely smooth and information spreads uniformly in all directions, the diffusion rate should match the surface area of a sphere, 4 pi r squared. Both continuous models predict faster diffusion than the classical inverse square expectation, but they are mathematical ideals, not physical structures. Even if space were perfectly smooth, its geometry would still control how information spreads. These continuous models offer useful comparisons, but the true structure of space must be built from discrete foundations. The path to predicting G. The discrete orthogonal model developed in Darwin's Machines 2024 predicts a diffusion rate of 4r squared plus 2. To estimate the diffusion rate for a discrete spherical model, we use a ratio method, comparing the discrete orthogonal model to the continuous orthogonal model, and then projecting that ratio onto the continuous spherical model. This predicts a discrete spherical diffusion rate of about 7.3 r squared. A spherical diffusion structure naturally produces an isotropic spreading, matching the observed symmetry of space more closely than an orthogonal lattice, which would be biased toward the x, y, and z directions. But no discrete spherical model has yet been built. Building that model could reveal the true geometry of space, and unlock the hidden structure that determines fundamental constants like G. Real-world modeling experience. Working on a discrete spherical model is not just about chasing a breakthrough. It's about building powerful, real-world research skills. You'll learn how to model discrete systems, how to design dynamic network rules, and how to solve real-world problems through original research. These skills apply across physics, materials science, engineering, computer science, and information theory. You'll be training in high-demand areas like complex systems modeling and simulations, areas that open real career doors, whether in academia or industry. And along the way, you'll be working on one of the biggest open problems in physics, the chance to predict the gravitational constant from the underlying structure of space. Ready to build your thesis? Start by reading Darwin's Machines 2024 and explore how information systems reshape our view of space. Then take the next step. Model the discrete spherical diffusion rate. Your work could become the first formal treatment of this groundbreaking idea. Be sure to cite Darwin's Machines as the foundational framework for your research, connecting your discoveries to the original discrete space network theory. If you have questions or you want to connect with others working at the frontier, feel free to reach out in the comments or through the links below. Let's build the future of physics together.